actually the best time or temperature to do this. And so I'm not sure if I'm going to go the whole 2 hours, but we'll see. Quantum computing is something that started in the beginning of the 80s, when the idea came up. And the idea basically arose from when people were thinking about simulating quantum mechanical systems on normal computers. And in around 82, Richard Feynman also had the idea to then actually use quantum mechanics to compute stuff. And quantum computing basically is about using quantum mechanical effects for computing. Well, what I'm going to talk about, I'm first going to go through a small example of the quantum mechanical effect. And then I'm going to introduce talk about what a qubit is, and I'm going to talk about quantum gates and quantum teleportation. And I'm going to just quickly introduce some quantum algorithms. And I'll talk a bit about quantum key distribution and then finish off with some implementation types and the current status of this. Okay. Unfortunately, I can't show it yet maybe at the end because I just got 3 polarizing filters, so we might still be able to show it. Picture the following experiment. We have a beam of photons, and we shine it at several polarizing filters. Like normal light is just arbitrarily polarized, it's not polarized in a certain direction. And basically what a polarizing filter does is it filters out one particular direction. Oh yeah, there's another thing. There's going to be a tiny bit of formulas in there, but if you don't want to look at them, just ignore them. It's fine. Okay, well anyway, we can describe random beam of light basically with the basis states like vertical and horizontal. But if I write this like this, what it basically means is that if this will be measured according to this basis, then we will get vertically polarized with probability A squared and horizontal with probability B squared, but don't worry about it. And it has to be in a state so that the total probability has to be 1, of course. Okay, what does the polarizing filter exactly do? Like I already said, it filters out basically a certain direction. And okay, this diagram is quite important for the rest of this talk. And basically what it does is it measures with respect to a certain basis. And then what happens? If you look at that little circle there, there's like an arrow pointing to a photon. So let's say this particular photon that comes into the filter is in a certain state. Described with the 2 bases that we just looked at. And basically if you now measure, it will be projected on one of the basis states. You can see that by the little dotted lines in the picture. And there you also have the probability again. So basically, what the first filter we're going to use now is a linear polarizing filter which will only allow photons through which will go in a horizontal direction, or rather, all the photons that will come out at the other end are horizontally polarized. So, of course, all the photons will go through that are already horizontally polarized, and if you look at that photon that's in the little circle here, it will then have a certain probability to also go through the filter. And it will, after that, be horizontally polarized. Okay. Picture the following thing. Right now we're using 2 filters. The first one filters everything out, like everything that comes out of the first filter will be horizontally polarized. Now the second one, rotated at 90 degrees, and it will do exactly the opposite thing. It will only allow everything that will go through will be in this state. So there's 0 probability for anything in this state to come out of the second filter. So now if we put these 2 filters behind each other, there will be absolutely nothing going to read back. Okay. Now what's the interesting thing here is what happens when you put a third filter in between the 2 already existing ones. And this is kind of important because it actually shows some of the peculiarities and it's maybe a bit intriguing. Okay, we have again the first filter. Everything that comes out of the first filter will again be horizontally polarized. Now we have the second filter, which is rotated at 45 degrees, and what this basically does is measure the beam in a different basis, and will then project what we're seeing again, but this time in the diagonal direction. If you look at this line below, or at the little diagram on top, so basically imagine everything is coming out, it's then going to be polarized in this direction. This is possible because you can, if you look at the formula below, or well, imagine the circle again that we had at the beginning, is that stuff that is like polarized in this direction and measured like this actually has probability of coming through here. Mainly, well, 1/2, but only not big one. Okay. Now the thing is, we now have, after the filter number 3 at 45 degrees here, stuff which is polarized in this direction. Now we use the third filter, which again will at the end have only things that are in this direction, polarized in this direction. Now the thing is, when we had the only horizontally polarized line, there was 0 probability for any of this line to come through the filter like this. However, now that we introduce the other one, we actually have stuff polarized like this, which does have a probability to go through the filter when we can work out. So actually there is no light coming through. And this is kind of the stunning thing, that if you have two filters which actually seem to cancel each other, and you add another filter in between, there is light coming through again. And this is actually one of the most intriguing effects, I think, anyway. And anyway, it illustrates a bit what's going on. Okay. Okay, what exactly are qubits? You could think of now, say that photon we just had. It could be, say, polarized in this direction or in this direction. And you can imagine now encoding, like, say, 0 or 1 as one of these states. So now we have a state which is either 0 or 1, and it's 0 with a certain probability and 1 with a certain probability. Basically, these states are the superposition between the two states. I mean, you could encode it in anything. You can encode it in photon, two photons like this, as long as they're a photon. Okay. So this is basically what a qubit is. It's just like a definition, and it can be projected into something like that. You might ask, what happens if we now have multiple qubits? Well, you can actually forget about that on the slide if you don't want to. I just put it there so maybe you can see how they combine, basically. Actually, oops. You can write the 0 and 1 if you want as a vector notation, again, remember the circle. And then if you combine two qubits, you can combine by a tensor product, which is something that maybe someone is interested. Okay. Now, what actually makes these qubits so fundamentally different than classical bits? One of the interesting things is that you cannot clone them just like that. You can't copy a qubit just like a normal bit. And basically, you cannot clone any on the qubit just like that. Also, if you measure, you actually disturb the state. So if you have some qubit and you measure it, you will get either 0 or 1, even if it has been a superposition before. This is actually also what happened in the filters. So say after the first filter, everything that came out has been projected into that direction and is horizontally polarized. What's also quite interesting is, say, if you have n particles, whatever we present in qubits, they actually span between the n-dimensional vector space, whereas classically they would be like 2 times n. I'll come back to it in a second. And also, what's really interesting probably is entanglement, and that is often used in quantum computation. Okay, apparently we can still show it later. Okay. Okay, so classically n particles, and you say you would represent it as a vector, and then just say you would. Then you can add them all together, and you have 2 times n-dimensional vector space. Say you have these spaces for the particles, and then if you combine 2 particles, you get the Cartesian product of particles. So you get this dimensional, it just adds up. But in quantum logic, we show it is basically one of the tensor product, so 2 n particles from 2 to the n-dimensional vector space. I mean, this is really not, forget about this if you want to forget about this. Like, I mean, in the whole talk, there will be occasionally things like this, but you can always skip these if you want to not get back to something more general and something. You know, the thing is, what this actually means is that there's an exponential growth of the state space for the system, and that's the thing that's interesting about that. Also, for example, there's states, take the state below, like there's 2 qubits, and they're basically saying in the position between these 2 states, 0, 0, and 1, 1. The intriguing thing is that this cannot be decomposed in a product of 2 individual qubits, and that's actually what makes the space so big. This is actually also what gets back to entanglement. And there is an interdependence between these qubits which does not happen like this with classical bits. Say we take here what's called an EPR pair. This is basically a superposition between these two states that we just already looked at. Now remember on the earlier slide we had like A times one state plus B times one state. This is basically the same thing. This is really nothing magical. This just means that you have 1/2 probability to measure this and 1/2 probability to measure this, so if you would want to decide. Now the intriguing thing is this. Say you have not measured anything at all. This state is just, I don't know, off the box. Nothing has happened to it yet. Now if you measure the first qubit, you have 1/2 probability to get either 0 or you have 1/2 probability to get 1. Now the thing is, say I already measured the first qubit. Say I've done this and I got a 0. Now if I would decide to measure the second one, then I would get the same result again. And this is really what's interesting about it. So basically, the measurement of the first one determines the next one. I mean, it's not like really a causal effect, but anyway, that's definitely what we're looking for. Okay. So, of course, in classical things, you can actually do things with bits, like certain gates, like the netting, or whatever varieties, or and in quantum computing, of course, you also have quantum gates, which basically fulfill the same function that classical gates fulfill in classical computing. However, already we said that each qubit can be written as a vector, so you can now express all these quantum gates basically as a matrix operating on a vector. These matrices are unitary, why this is, don't worry about it now. But the most important thing is that quantum gates are reversible. So any gate can be run from one end and the other, and then backwards, which is not the case with classical gates. Because remember, in quantum computing there is no such thing as a fan-in. For example, in the classical case, you have an OR, so you have like one line and another line, and you just OR these two bits together and you get an output. This computation is not immediately reversible, which is a very big difference to quantum computing. And again, you have no fan out of the gates, because remember, you can't copy them. You can't, cloning is not generally possible. Okay, this is, I just put this here because I used them later in the example, but you don't have to remember any details. Basically, these are some of the commonly used ones. The identity, which does basically nothing. The negation, which flips to 0 and 1. The phase shift, which does 0 to 0 and 1 to -1. And then there's combinations like the Y below. Another very important gate is the so-called controlled NOT gate, which is really very simple. You have two qubits, and one is used as the control qubit. And depending on the value of the control qubit, the other qubit will be flipped or not. So say you have 1, 0. Say we use the first qubit as the control qubit. And here, it will be flipped. Whereas if the first qubit is 0, like there, nothing happens to the second one. So that's really all it does. Then you might have wondered, like, if I make a quantum circuit, how do I get all these superpositions? And there's something called, for example, the Hadamard gate, which will create a superposition between those. So basically, you'll just map a 0 to a superposition like that, and you want to. I mean, this is just a first example. Okay. Now, what can we actually do with it? The first thing, which might be interesting, remember, if you measure the stable collapse, so actually, if you measure one qubit, you will really get only one classical bit at the end. So the question is, how do I actually get anything out there? One of the interesting things, for example, is you can use one qubit and one shared EPR pair. Remember, we have the EPR pair, like the 1, 0, 1, 1, and 0, 0. And basically, we can now share something. I keep the first qubit, and I move the second qubit to 0. And then we can use this later for operations. And there's, for example, one thing which is called dense coding, which I'm not going to go into detail, but it occurs quite often. one qubit and one shared EPR pair can be used to transmit 2 plus coordinates. Okay, maybe I'll skip this. I don't know if everybody is really interested. Alice and Bob basically share one of these pairs, and Alice has 2 bits that she wants to transmit, and 2 bits basically give you a certain value, and it's 0, 1, 2, or 3. And then Alice just picks one of these transforms that we just looked at a couple slides ago, depending on what the number is, and applies it to her part of the EPR pair. And her part of the EPR pair, I'll just mean the first qubit now that she has. She sent it to Bob, and Bob does some further transformations and can retrieve the 2 bits that we need. What's maybe more interesting or more daring, because it has more of a buzzword character, is quantum teleportation. And the idea behind teleportation is very much like in Star Trek, where you can, or maybe like, you can teleport one person from the moon to the Earth. It basically means teleporting a quantum state, like 1 qubit basically, using 2 classical bits. And this is like, again, this is real teleportation, just again, we can't copy anything. Okay, this is the only thing I'm really going to go into detail. Okay, we start out with a state to be teleported. This is just an arbitrary qubit, and Alice has this qubit. And Alice now wants to send this qubit to Bob. Now, a long time ago, Alice and Bob met somewhere, and they shared an EPR pair, and Alice kept the first qubit and Bob the second, just in case they ever wanted to do anything like this. Okay, so we have Alice, and we have Bob, and we have the EPR source where they get their shared EPR pair in the beginning. At the bottom, what this basically is only what I've just said. So Alice has her input, the qubit that she wants to teleport, and there's the EPR pair. That's like the whole state, also the part that Bob has. So basically you can write the entire state like this. If this, okay. Well, anyway, this is basically the qubit that she wants to teleport, and this part comes from the EPR pair. Okay, what does Alice do now? Alice applies a CNOT to the first 2 qubits. This is like the qubit she wants to teleport to Bob, and her half of the EPR pair. Remember what CNOT does? It flips the value of the second input depending on the first one. So say here, in this case, the qubit to be teleported would be 0, so nothing happens to the EPR pair. In this case, it's 1, so we flip the first qubit. Okay, now Alice can use the hierarchy that we already discussed to create a superposition on the first qubit, then the one she wants to teleport to Bob. And remember, this is exactly what it did for a 0, and this is exactly what it did for 1. This part is in quantum. You can rewrite this too, you just have to trust me that you can rewrite it into this form. And basically it's saying you would know measure. So we have to state that you would measure. The first 2 qubits, so we're talking about these here. Actually, I mean, these are not like individual qubits, but possibilities for the first 2. So say we measure 0 and 0. Say Alice will take this and measure it. Then Bob's half of the EPR pair, that was left here, would be in this state. If she measures this, it would be in that state. If she measures that, this one has to go. So this is summarized here again. So Alice actually measures the first 2 qubits and sends the outcome of the measurement to Bob. So she measures that, gets this, and then sends this 2-bit value to Bob. Now you might already know that this is actually the original state of the qubit that we wanted to teleport in the first place. So if Bob gets a 0, 0 from Alice, he doesn't have to do anything because his qubit will immediately already be in the state. If he gets any of these, he has to try any of these transformations to basically fix his state to get it back. So basically, it does the same thing again as what before. We use these transforms and we use the 2 bits to indicate which ones we're also going to use. And then Alice has been teleported to Bob. Okay.
in this process, when Alice sends her qubit to Bob, the communication is still subject to the normal sort of relativistic limits. So she can't send it faster than the speed of light. But the interesting aspect is that the change of state between Bob's path and the EPR pair is instantaneous. That's true. That the whole process is a mixture of conventional communication and quantum change of state, which doesn't involve any relativistic.
Alice has to send these two classical bits, of course. I mean, there is no faster than that. I mean, this is also part of the EPR paradox, but I decided not to put it in here. Okay. Now, what makes quantum computing also so interesting? I mean, what can we actually do with this? The interesting thing is, of course, the superpositions that we already looked at. We can now compute things on the superposition of values, say, simultaneously. So basically, say we take an input of all values that any function or whatever you want to do has, and we can then apply a function and compute it all on all values simultaneously. Now you might say that's really cool, we can do everything in one step instantly. But remember that measurement only has a single output. So if we then say we have a function that takes only two values as input, 0 and 1, and then we can calculate the function of both inputs at the same time, but if we measure, of course, we will get only one output. So you might wonder, so what good is it anyway? Most of the algorithms still make use of that parallelism by calculating some common property of the function. For example, in the hodgepodge algorithm, basically the question is, I have a function and it's either balanced or constant, and you have to find out where it is. In the classical case, of course, you have to send at least more than 1.5 to find out. In the quantum computing case, it's not the case. Actually, at once. If you just find it, then you're using this kind of technique. Another technique that's used is that to make one output very likely, which is, for example, used in Grover's search algorithm. Well, this is basically just a picture of what I already said. In general, say you have some function, and basically this is how you transform things. So say you want to have a function that takes only two values as input. So you, for example, use a hierarchy to create this superposition between 0 and 1, and apply the function. And basically here, so you put 0 here, you can get at the output of one particular thing. And that's what the technique is also used, for example, with research. Okay. There's quite a number of quantum algorithms. The most famous one is really the Schwarz factoring algorithm because of its implications for input. There's also the search algorithm, hodgepodge algorithm, and there's plenty of other things that are really like specific to one particular thing. Just remember that it's no longer quantum computing, and also programming in quantum computing is also something that is not, say, yet done. So all these algorithms really like construct these kind of gates to make computation very specific. Okay. What does Schwarz factoring algorithm do? Basically, it allows factoring in polynomial time. Now, this means that it's like what it's called like an easy problem. Whereas, for example, in classical computing, it's called a hard problem. So basically, for example, if security RSA depends on the assumption that factoring is a hard problem, because otherwise you can basically factoring is something you need to do if you have a secret key from what you already have, the public key. And so if you could build a quantum computer, this would be a relatively easy problem, and I would no longer send PGP emails for them. Okay, I'm not going to go into details of this algorithm. I'm just going to mention a couple of things that are key points that are important. Basically, the important thing is to reduce factoring from the period of the function, and it again makes use of the superposition thing that we already talked about, and it makes use of the quantum Fourier transform, if you want to. like I already said, another famous algorithm is Grover's search algorithm. And Grover's search algorithm allows an unstructured search in Square and or search. Now, an unstructured search is basically a search where there's no inherent, not exploring any inherent structure of the problem. You just have a totally, say, chaotic heap of things, and there's really no structure. Like, for example, if you have a list of names or something, or I don't know, you would try to solve a path diagram or something. And there's no structure you can use. So you can basically also means that you can use it for any search. And classically, if there's total chaos, you have to walk through all the things and look like, is this what I'm looking for? No, is this what I'm looking for? So in the worst case, you end up looking at all things in your farm. Whereas in quantum computing, you would only have to look at square root of n things in your farm. This has been extended to give the fact that true speed, okay, that's not a lot, but it's so interesting. On any brute force kind of search you have to do, for example, like this or a random or any other picture. Better results have been achieved in quantum computing using structured programs, for example, Hawk's algorithm. But that's then, again, not generally applicable. Okay. The main outline of Grover's algorithm, again, is not your details. First of all, you prepare a register containing supervision of all possible values. So say you're looking at some kind of file of things, and basically you put all these pile of things, these things in the file in a superposition, or like if it's values of a function, you put all of them into a superposition, like we saw it when you can, for example, using watermark gates. Then you compute the desired search criteria for each value in parallel. What this just means is that say I have this function p of x, and all this function really does is it takes x, something in the file, and it is 1 if that's what I'm looking for, and otherwise it's 0. So it computes this for all values for all values that of the function or in the file in parallel on this superposition input. What is done now is that if this is 1, so this is one of the things I'm looking for. First of all, the amplitude is negated. What does it mean? The amplitude is the probability amplitude. This is like the A and the B that we saw in the beginning. We have like A 0 plus B 1 giving the probability of measuring one of these states. What is then done is applying inversion by the average, say A here is the average. Of course, we've just negated the A. So this makes the amplitude of the states where we're not looking for much smaller. What this basically means is that we're making it a lot less likely that we measure anything we're not looking for. And we make it a lot more likely than if we apply measurement that we will get what we actually want. Okay, this is repeated this number of times. You might wonder why is this exactly repeated this number of times. I'm not going to go into that, but it's actually interesting if you look at it. Because remember the circle we had at the beginning? Basically, all the quantum operations can also be described as rotations in our high-dimensional vector space. So actually rotating closer to what we're looking for, that's it. And at some point you will rotate further than, rotate like away from what you're looking for. So this is actually the optimal number of times to do this. And then you get the result with a very high probability. Okay. Okay, one of the interesting things, also because it's already been put quite into practice already, is the quantum key exchange. Basically, the key exchange is means Alice and Bohr exchange the key that they will then use for further communication, to encrypt further communication. So the thing about quantum key distribution is not that you can actually prevent someone else from eavesdropping on you and getting your key, it's that you can actually find out if someone did, and then you can of course create your key. The thing to note that we already saw before is that if say Eve is the one who's trying to intercept. As usual, Alice is wrong, because that's for no reason. Eve cannot clone the transmitted states. So she cannot just make a copy of the qubits and measure them independently or do other transfers on them. And Eve cannot distinguish between autonomous states without disturbing the states. So basically, if Eve
Casey just intercepted, pretend to be Alice to Bob, and reset it back to Alice.
you mean like a manual thing?
Yes.
Well, she could. But, I mean, this basically is a key exchange and not a, it's a series that you normally identify with a person. Like, for example, what they use this for is also in satellite stuff, you want to use it? And I mean, you could of course then afterwards do some kind of organization. I mean, this is really just for exchanging a key. You could then later authenticate basically. But for example, this could be like exchanging a key or exchanging a module or something like that. Okay, say if Eve would not look at it, she would disturb the quantum state, and then Alice and Bob can find out about it. Okay, so we have Alice and Bob as usual, and Eve. And Alice and Bob share one classical channel and one quantum channel. Now, in order to say Alice and Bob now want to exchange some kind of session key, so Alice picks a random key. And she will now encode each of the key bits of the key, either in this basis or in this basis. So basically one way to do this is say she would generate some random bit string B, and if the bit on a certain position is 0, she chooses this basis, and otherwise she chooses this one. And then Alice uses the quantum channel to send these qubits to Bob. Let's first look at what happens if there's no Eve does not occur. Once Bob has received these qubits, he announces that he has received the qubits. We'll see in a moment why this is important. And then he measures the state of the qubit by randomly picking one of the bases. So either this one or this one. You just say with probability 1/2 picks either one of them. You say you could also, for example, generate one of these bits things B of its own and do the same thing. If one is 0, it picks this basis. If the bit of the position is 1, it picks this basis. Okay. Bob now has the qubits and has measured them. Alice now tells Bob which basis she used to encode the qubits. Of course, Alice should never do this, of course, before Bob announced that he received the qubits, because otherwise Eve could use the same information earlier on. Bob and Alice now throw any of the measured qubits, like the key bits, away, for which they used a different basis. So basically, you could say they exchanged their random string B, they used to pick the basis, and for everything away where the basis differs. And they used them all the remaining. What's left over, where they use the same basis, they use this as the key for further encryption. Say, for example, if they have an average of 50% chance that, say 50% of the bits, the qubits they exchange will actually be the qubits. Say if they pick probability 1/2 and average they will get about half of the bits usable as qubits. If there's less, then just say protocol will just add one else. Okay, now let's see what happens if Eve actually listens in on the communication and taps. Eve is just in this case like Bob. She also just picks a random basis and measures the intercepted qubit. Again, like Bob, she has about a 50% chance of picking the right bases because we have 2 bases. What Eve basically does then is measure the qubit. So if she now wants to resend it onto Bob, she actually has to re-encode the qubit, and she just picks the basis she used to measure it. Of course, if there's a 50% chance that it's actually not the basis that Alice used in the first place. So what this actually does is introduce quite a high error rate. Say Eve picked the wrong basis, but Bob picked the right one, so the same one as Alice, so we will actually try to count this as key bits. Then Bob actually has a 25% chance to measure the wrong value. You might ask, why is this 25%? Say Alice picks this basis that we had at the very beginning, say she uses this kind of basis, and now Eve will say pick the wrong one and use this one instead. Measure the qubit, re-encode it like this. Now say we are in this particular state now. If Bob now uses the right basis, it will be projected on one of the basis vectors like this. So basically Bob again has a 50% chance to get any of these. So there's a 1/2 and 1/2, 25% chance that Bob will get the wrong one. Okay, now how do they detect this? Half of the key bits that they harvested from this method, they will now tell to each other, say Alice picks n of these 2n key bits, and send them to Bob. Then they compare the splits, and if more than a certain number disagree, they know for certain that Eve is basically observe the state, and they just have to sign them. And you might wonder, like, why this is like a certain number, because if there would be no error, then if there's any errors, then they should add one. I mean, this is like a kind of simplified protocol, because in reality there can be other disturbances, and there's like error correction being used, so this is one, this is there. And if you're interested, there's have a look at these protocols on the web. Okay, now about implementation. I have to admit that I see this quite from a computer science perspective because I'm not a physicist. Basically, what makes it so difficult is that quantum states get disturbed, if you like that, in the wild, so to say. This is called decoherence, and this basically means that the quantum state gets disturbed, or say changed if you measure it. Say if you go past the random polarity standing here, it will basically disturb. And so this is why quantum states need to be isolated, so you can actually do all these things with them. And this is actually being solved algorithmically, not in hardware, by what's called quantum error correction, if you don't have to look at it. And of course, I mean, you might have read that there are some small scale quantum computing devices already, but scaling is a real problem. I just want to briefly have a short look at implementation types. I don't want to go too much into it, because like I said, I'm not a physicist. The first one is nuclear magnetic resonance, and what they basically do here is use a microscopic amount of matter, say like an atom or something, and like atoms, and the qubits are then encoded average spin state of these atoms. And if I then want to do operations on them, I can use a magnetic field to change the spin state. I mean, actually the 2 biggest quantum computers that have been built so far both use this method. And although it is believed that it will not actually scale more than about 15 qubits if one were to pursue this kind of implementation. Another method is called ion trap, and qubits are basically represented by ions which are trapped in a magnetic field. And then operations are performed by shining laser on ions. The downside of this method is that it needs to be really, really cold. So, for example, having an ion trap quantum computer here on the field would probably be very difficult to learn. So there's also solid state implementation. Well, anyway, another method is what's called solid state, and qubits are encoded in a spin-off phosphorus nuclei, which are actually in silicon. and there's actually quite a lot of people also in Australia, for example, like in Istanbul, who try to pursue that kind of alley. Because they're hoping that it will scale a lot higher than just the 15 qubits that we had before. And if you then want to do operations on this, they also again use electromagnetic fields, or for example, if you want to change the spin state of one of those nuclei, they like the radio pulse. Another one is optical. Qubits are represented as photons, for example, like we had before already. And in the polarization thing, you could say that polarized in one direction is 0 and polarized in the orthogonal direction is 1. Or you can also do it between different models, but that's quite physical. Operations are then performed by beam splitters or phase shifters. Actually, this is actually like all the quantum key exchange things, they use photons to represent qubits. Okay, now like I said, they don't really scale very well. So currently there's only a 7-bit qubit quantum computer. That's the biggest one that's built up to date. There's also a 5-bit one at IBM. I think the URLs are quite hard to read. Are they? Anyway, just come to me afterwards if you want to look at it. These both use nuclear magnetic resonance, like I already said. There's a lot of people trying to build a quantum computer. For example, in Australia, they're also trying to do the solid state approach. Or like in Germany, they're more also into the ion trap thing, but there's really a lot of people working on it. So if you like type it into Google, you'll find so many universities who are all trying to build quantum computers. About quantum cryptography, things are a bit more, well, let's go. Actually, about quantum computing, it is expected that there will be no quantum computer in the, say, like tomorrow. But, hopefully at some point there will actually be implementations. You can maybe compare it a bit to like the beginning of computing, when they were saying, oh, at one point we will be able to make a computer the size of a room, which is, it will take a long time, but hopefully if quantum mechanics is correct, this will all work eventually. What's a bit more practical right now is quantum cryptography, because there's a lot of people who have done it in the lab already, like in Geneva they did it, and at the Toshiba lab in Cambridge. And there's also a company that claims to actually put a working device on the market at the end of this year, which I don't know. But they're at this URL. The thing is, for example, these things, currently the maximum length they can do quantum key exchange over is around 100 kilometers. Because remember also like things like, copying a qubit and repeating it somewhere else, or putting it, transforming it into something else, it's not that easy. Maybe with quantum teleportation, but otherwise, scale is quite limited up to now. But anyway, this is quite interesting because it's gonna happen like soon. Yeah, there's a question up here.
So couldn't you enhance the distance by putting repeaters in and then calculating the amount of more wrongness? This is like, if you put a repeater in, it's just like putting another eve in. So you know that you will lose another 25% per repeater. So couldn't you travel the whole world just by knowing how many repeaters are in the middle?
Maybe, but the thing is also that the quantum states are really very fragile. So any disturbance will make sure you don't get any qubits. But I don't know, it might be possible at some point also with quantum error correction to achieve larger distances, but maybe not.
Hello? Compared to the complexity of this technology, how easy is to have a denial of service attack of this technology?
Well, say we go back to Alice, Bob, and Eve. If Eve would keep measuring infinitely, they would never exchange any keys. But I think there's a denial of service in almost anything. If I go there and smash it with a hammer, this will probably be very effective.
if I understand correctly, quantum cryptanalysis can potentially break factorization is a hard problem type cryptography, i.e. RSA. But quantum crypto will only bring us security back if we can actually have a means of transporting quantum state to our partners. So, whereas I might lose RSA to quantum cryptanalysis, I then need to bury fibers or create line of sight laser connections to all the people that I want to talk to.
Yeah, line of sight, yeah. Well, I guess.
Or have some means of transporting quantum state.
Yeah, sure, if you could, yeah, sure. I mean, if you could transport quantum states, you could apply the key exchange that we just looked at.
Okay,
So you can just use a new mean to encrypt your stuff.
what are the present means of transporting quantum state? They are optical fiber, laser straight through the atmosphere?
I don't think there's any that runs through the atmosphere, actually. Are there? Yeah, could be. Okay.
That's it, basically.
Yeah. Yeah, sure, yeah.
I have a question first concerning scalability. In how far can we be confident to some level that there's scalability beyond some limit at all? Because there's still this problem, the gap between quantum world and the usual measurements that is, as far as I know, not really solved. This decoherence problems of quantum chaos and so on. So in how far can we be sure that the scalability to a level where this is really usable? I mean, to really attack the RSA, you have to be able to factor quite large numbers.
Yeah.
Is that all possible?
Hopefully. I mean, I'm optimistic, so I say yes, but I mean, I might be wrong.
That's all.
Well, I don't know. I mean, there will be something else, and there's a lot of other things you can do with it, so I still think it's very interesting. I mean, there's also maybe some nasty applications to this, because remember I also say, if I could translate, so for example, some people have been trying to find means to use this for, say, music transmission or software transmission, especially software, because it's going to be one use only for sure. But yeah, I don't know. I mean, this is like far in the future, so yeah. This is actually a really cool book. If someone is interested in that, I also have it here if you want to have a look at it. This one is a bit more. Well, this one is a bit more technical. This one is a bit more easy to read. This one is a PDF you can just download somewhere. There's also www.qubit.org, which has about 1 zillion links to all kinds of information if you're interested. There's also QC Australia, which has a lot of stuff. And if you just want to like play around with it a bit, there's several simulators. There's also some for Mathematica or for Perl or Haskell. Just have a look at your URL if you want to get it. And I think we can still do the.
What you really need for this is, of course, something like an overhead projector and 3 large polarizers so everyone can see. We only have 2 polarizers here, but I remembered that my laptop LCD screen also puts out polarized lights, so that can act like the first polarizer. Can everyone see the screen? Well, in that case, the people in the front are lucky, and everyone else has to maybe come forward later and I'll show it again. Okay. This is the first polarizer. As you can see, there's still light coming through. It's a little bit darker because it filters out about half the light. If I turn it, at some point no light comes through anymore. Now the polarizer is crossed to 90 degrees to to the light which comes out of the LCD. I can do the same with the second polarizer. Now I have to like circles. Now if I put them behind each other, it is still black. And now I rotate the middle one, and we have light coming through again. It's faint, I'm not sure if it's visible. And now if now you should be able to see it clear. So what you have here is, with 2 filters, there's no light coming out, and with 3 filters, there's only some light coming out.